Hi, hello, welcome to Warm Sphere, and this is a first video on Warm summary on the topic of reinsurance. In this very first part, we're gonna talk about reinsurance arrangement, which consists of a proportional reinsurance, excess of loss reinsurance, and the reinsurer conditional claim distribution. So let's begin. Okay, in this chapter, we are gonna talk about four of random variable. Okay, we are gonna first introduce three of them here. First one is x. I will use to represent the original claim. Amount, the original claim amount. The y is the part of claim that will be paid by direct insurer. So I may refer to this y as when in this lecture, and this z is the part that's gonna pay by the reinsurer. Okay, so it is true by sense that the original claim would be equal to this y plus z, because the original claim would be reimbursed by these two parties, the direct insurer and reinsurer, right? Okay, so let's first have a look at our first model. We call it the proportional reinsurance. In this model, the y will equal to alpha x and z will equal to 1 take away alpha multiplied by x. So for each claim that come into our company are gonna share in the same proportion, no matter how big or how small. As we see from this figure, this is when alpha equal to 75%. So the white part is for the part that paid by direct insurer. We can see that all of them have just similar, right? So it's easy. Okay, so and this alpha is referred as the retained proportion or the retention level. Okay, from this model, the conclusion that we can be drawn is the expectation of y is the alpha multiplied expectation of x, which is true by take expectation to this equation. For variance, we could do that, but the alpha gonna be alpha square. For skew, it's gonna be alpha cube. Okay. However, the coefficient of skewness is dimensionless quantity. So the coefficient of skewness of y will be coefficient of skewness of x. Okay. And if you want to do, you may try to figure out expectation of z, but this can be done in a very similar way, so I just gonna skip it. Okay, and have a look at our question, our problem of the chapter. So in this problem, we are given 8 claim amount that paid by reinsurer. This is the claim amount that paid by reinsurer, and we are told that the original claim amount are modeled using gamma of alpha lambda. We use alpha equal to 80%, the retained proportion, right? And we are asked to find the distribution of reinsured claim and estimate the parameter alpha and lambda using method of moment. So we have to answer question here. Okay, so let's do it. First of all, we have that x follow gamma of alpha and lambda, right? We have z equal to 0.2x, which means z equal to 0.2x x gonna be 5z, and of course dx will be 5dz. Okay, so if you consider the integral of PDF of x, right, we're gonna have this. This is just gamma alpha lambda. This one. And now you substitute x with 5y. So we're gonna have, instead of x here, we have 5 z, I'm sorry, here, and e to the power of this one, and instead of dx, we will have 5dz. Okay, so we're having this, and then we have a look here. 5 to the power of alpha, take away 1 with this 5, we're gonna have 5 to the power of alpha, and then we can combine with this lambda to the power of alpha. So we have alpha 5 lambda to the power of alpha over gamma alpha z to the power of alpha, take away 1, e to the power of negative 5 lambda z dz. And this is integral of PDF of z. So we can see now that z is follow gamma alpha and 5 lambda, right? So by using the method of moment, first we have a look into our table. We found that expectation of x is just alpha to the over 5 lambda. Oh, not x, sorry. Expectation of z. And expectation of z square is alpha multiply alpha plus 1 over 25 lambda square. Using method of moment, this can be estimated by sigma x over n, and of course this is gonna be sigma x squared over n. So you just plug in this 8 number into your calculator and calculate out. We're gonna have here 12.65. This is gonna be your first equation, and the other one is 264.8775. This is gonna be your second equation. So you may try to solve this equation system. So let me give you a little bit of how to do it. We take square of the first equation over the second equation. When we do this, the 25 lambda square are gonna cancel out, and you will have just equation of one variable of alpha. So it's solvable, right? So you can solve this one, but I will leave you to be just to do it yourself. And finally we will have alpha equal to 1.52613 and lambda equal to 0.02413. So let's try it. Okay, then move on to the next topic. Now we're gonna discuss the other model for the reinsurance, which is excess of loss reinsurance. In this type of reinsurance, they're gonna split using proportion, but instead we had M, we call retention level. So be careful because we call it the same. This one is called retention level too. So be careful whether we're talking about excess of loss reinsurance or the proportional reinsurance, okay? Because they're using the same word here. Okay. The way it works is when loss less is not excess this retention level, so x is less than m, the direct insurer will pay full amount, and there is nothing to do with the reinsurer. Okay, but when the claim amount is excess of this retention level, the direct insurer will pay only the loss to the retention level. The rest of them gonna pay by reinsurer. Okay, so this one is good for the direct insurer because the direct insurer can ignore the significantly high amount of claim, right? So it obviously reduce expectation and hence reduce the variance. Uh, Sometimes the reinsurer may pay with upper limit, so they may pay with limit of 10k, say, so excess of M by 10k gonna pay by reinsurer, and then over that again gonna back to the direct insurer. So let's have a look in this example. So we are saying that we're gonna write down the expression for y. The direct insurer pay for if the layer between M and 2M is reinsured. So the reinsurer only pay M in excess of M, right? So let's see. We're gonna pay full amount of X, right? If we not yet reach to the retention limit. And then we're gonna pay just retention limit is we have excess this retention limit but not yet excess the upper limit. And lastly, if the original claim is excess the upper limit, so only the layer between M and 2M is reinsured, so reinsurer gonna pay just M. So we're gonna pay X, take away M, right? And that's it. So with this excess of loss reinsurance, we can draw the following conclusion and expression. The expectation of Y will be consist of two parts, which is the part that not exceed the retention limit and the part that beyond the retention limit. The second moment could be calculated in a similar way. The variance, the moment generating, just follow the formula. And the same thing go with the reinsurer. So it's worth to mention here that if you have an option, because you know that expectation of X, Y, and Z connect by this equation. If you have an option to select between calculate expectation of Y or expectation of Z, you would prefer Z because you're gonna do just one integral. Because the claim that not beyond the retention limit, they have nothing to do with the reinsurer, right? Yeah. And for the rest, it's just follow the formula, so you just read it. However, variance is not gonna be the sum, not in the same way of expectation, because Y and Z are obviously not independent. If X take a log normal or normal distribution, we have a result to help with integration. But this is the topic for the next chapter, the next part of the clip. Okay. So let's have a look at this figure. This is figure of claim that come into excess of loss reinsurance system. So let's say this is the reinsurer gonna pay 30k in excess of 20k. When the claim of 30k come into our company, we pay the 20k, the first 20k part. The 10k, the rest of them go to reinsurer. If it's just This one I guess 15k. This one not even reach 20k yet, so we gonna pay all of them, right? But if the loss of 55k come to our company, we have to pay for 20k the first part, and the part that excess of 50k, because the reinsurer are gonna pay just only this level. So this is how it works. Okay, so let's see this question. This question is asked to find expectation of y when x have Pareto distribution with parameter lambda equal to 200, alpha equal to 6, and m equal to 80. So we're not gonna calculate it directly. We will calculate using this one because we prefer to calculate expectation of z rather than y. Expectation of x, the Pareto is just lambda over alpha take away 1, so we have 5 here. Expectation of z is integral from the retention limit to infinity, x take away 80. Then the PDF of x, which is alpha lambda to the power of alpha over x plus lambda to the power of alpha plus 1 dx. Here we do a substitution a little bit. We substitute x, take away 80, augment 80 by z. We're gonna have, instead of x plus 200, we have z plus 280 dz, right? And we adjust the integrand a little bit, so we multiply 280 to the power of 6 and then divide it, so it cancels out to be 1. So everything gonna be the same, but the integrand change to be this one, right? And as you might realize by now that this one is just expectation of a Pareto with lambda equal to 280 and alpha equal to 6. So all of them will be reduced to just one simple expression. This simple expression, right? So you just plug in this number into your calculator and you will get 32.5626. Okay, so let's talk about the last part of this clip, the reinsurer conditional claim distribution. What is it? I have told you earlier that in this chapter you're gonna see 4 random variable. This is the 4th one. This variable is the claim paid by reinsurer, but given that the insurer have something to do with the claim. Okay, we interest in this distribution because sometimes the reinsurer, they don't know how many the claim that actually are, because they only see the one that they are paid. So the distribution for them gonna be different, right? And that is our W here. So when we're talking about P of W is less than W here, right? That means P of X take away M gonna less than W, right? Given that X is more than M. This is the probability that X is less than M plus W over 1 take away f of m, right? And the upper one, we could, oh, I almost forgot. And x must be greater than m2. Okay, we have this one. So the upper one can be written this way: the integral from m to w plus m of fx, right? And the denominator remain the same. The denominator is 1 take away f of m. Okay, and this is the distribution function, right? So to find the PDF, we take derivative, and hence we will have the PDF of w can be calculated using this one. This is distribution for w. Okay, so you may thinking of it this way: is equal to z, given that z is more than 0. So you can have this one too. You can have expectation of w is an expectation of z, but given that z is more than 0, so it's equivalent to x more than m, right? Okay, so with this result, we have two questions. First one is, what is x is exponential lambda for the distribution of w? Okay, so dw is f of w plus m equal divided by 1 minus f of m, which is equal to lambda e to the power negative lambda w plus m over e to the negative lambda m, right? And it's going to cancel out this part. E negative lambda m gonna cancel out, so we have lambda e to the power negative lambda w, which is still exponential with lambda. And this is what we could expect, because the exponential distribution has something called memory less property. Okay, so let's have a look for the Pareto. For Pareto, g of w is, just first copy down the formula and then have a look into the table. This one is the PDF first. It's gonna be this one, right? This is PDF of Pareto, and then we divide by the distribution function of m, which is lambda over lambda plus m to the power of alpha. So lambda to the power of alpha will cancel out, and we have alpha lambda plus m to the power of alpha over w plus m plus lambda to the power of alpha plus 1, and this is Pareto with parameter alpha and lambda plus m. So we just plus m to the second parameter in this case. Okay, so let's see our conclusion. So our conclusion is g of w can summarize into this formula, and expectation can use in this formula. If x is exponential, then because of memory less property, the conditional claim distribution for reinsurer is still exponential, and the Pareto gonna shift by m in the second parameter. Okay, and then before we end this clip, this is our last question. It's quite long question, but we're gonna work it out together. Okay, we are asked to verify which of these statements are true. Okay, let's see. The first one, expectation of z is the integral from m to infinity of x take away m fx dx. This is true, of course. This is absolutely true by definition, right? Okay, so let's see number two. Number two, let's try to work on a little bit, because we have e of z equal to e of x take away e of y, okay, which equal to e of x take away e of y is integral from 0 to m x fx dx, and the other part m to infinity m fx dx. So we want integral from 0 to m, but m take away x and this m. So to get this m, I think we have to add in this one in. This is the one that we have from the last line. We keep this one in to fulfill it, right? And because we take away, we have to plus it back. Right? And this part, this is one big M. So we now have e of x take away m, and these two parts can join together because they have same bound. So it's gonna be plus 0 to m take away x fx dx, which is exactly what we are asked to verify. So this one is true. Okay, let's see the third one. The third one is true or not. The third one, the expectation of z is equal to integral from m to infinity 1 take away f of x dx. Okay, so how we gonna work it out? This one we have to get it back to form of PDF, right? So we will try integration by part. Here m to infinity 1 take away f of x multiply by x pound dx. So we have x 1 take away f of x from infinity to m, take away integral of 1 take away fx dx from m to infinity. No. Because this one is already differentiate x. This one we're gonna not differentiate x, but instead we differentiate the first one, so we have this one. Okay. And the first one the first one is when you substitute infinity in, because f of infinity gonna be 1, so it's gonna be 0. So we're gonna have minus m 1 take away f of m plus integral from m to infinity x f x dx. And then this from the first one we could write this in square bracket instead in integral form. So we have integral from m to infinity m to infinity fx dx. So now we have same bound for the two integrate, so we can just change the inside. We combine it. We have integral from m to infinity x log x take away m fx dx, which is the first one. So this third one gonna be true. Let's see the fourth one. The fourth one is obviously false, right? Because I think I better show this one. Because the integral from 0 to infinity of 1 take away fx dx, we just done the same way using by part. We're gonna have integral from 0 to infinity x fx dx, which is expectation of x, right? So this one can be the one in number 3, this one plus m, which is not be the same thing, is m is not equal to 0. So we can tell that this one gonna be false. And because of the same result, this one is m equal to 0, right? So this one must be true. So what about number 6? Number 6, we just substitute x minus m by z from the first one. This one, we just do use substitution. We have instead integral from 0 to infinity z f of x f of z plus m dz, right? So this one true. And the last one, we have seen the last one before. The last one, it is conditional claim, so it's not z, it's w. It's not respect to the original claim, but the claim that reinsurer involved. So this one gonna be false. And here we done. We verify the seventh statement. Okay. So thank you.